Hello, everyone. I'm Nikos Pantelaios, and today I'm going to present to you FV8, which actually is pronounced favorite, if you put a lot of imagination into it, which is a JavaScript engine based on V8 to detect evasions. So the first question is, why evasions? Why are we looking into that? And the simple answer is that evasions can be behind malicious behavior. So a very basic example of an evasion is an IP evasion. So if the IP is from a university, I will not show the malicious code. But if it's from a user, I will show the malicious code. And we have seen that evasions tend to be present in top malware categories. And they tend to be also more and more sophisticated as time goes by, which makes studying them very important. And in this talk, we're going to talk about JavaScript evasions. And here is that because of the dynamic nature of JavaScript and how they load the code during execution, that this makes evasion a very good tool from a malicious actor to use. So what is the gap that favorite wants to bridge, basically? There has been previous work on doing forced execution. But the problem is that it has either been done on an outdated browser. For example, Rosal did this in Internet Explorer. And they also used deprecated APIs. Other work hasn't open sourced their code, or they haven't done their execution in Chromium browser and the V8 engine. There are also tools, dynamic execution tools, that are outside the browser. But one thing they may be missing here is that they cannot get the whole chain of injections and how the code is dynamically loaded continuously. And this is where our tool comes to bridge this gap. So basically, some of the advantages of our tool is that we are making our patches, our modification, inside the browser, inside Chromium. And that means that no matter how many levels of injections you have, that you can still capture the whole code execution. And we are applying forced execution based on a list of APIs, that those APIs are related to dynamic injections. And this list is modifiable, but we'll talk about this in the future. And we are making our changes during the parser level of the Chromium execution at the AST node level. And this gives us a system with low performance overhead and low false positive rate in the evasion detections. And one of the biggest benefits is that it works with a multitude of systems, as G. Hunter also mentioned before, whatever is the base of V8. So we're talking about Chrome extensions, NPM packages, phishing, or other type of web pages. So in very simple terms, this is what our architecture looks like. So we're making the changes in the AST level, and we're force executing some additional blocks. This leads to higher code coverage, and we automatically flag the evasion, the evasions that we observe. And because of the higher code coverage, we're also exposed to more malicious code. So an evasion can potentially lead to malicious code. And we semi-automatically detect malicious code also. And if you want to see the full architecture, this is what it looks like. We're not going to dive deep into all of these elements. The main components that you may want to be aware of is the NPM module and the Chromium module that we're doing the implementation of our patches. This is where the forced execution happens. We also have a post-processing module that takes what we forced execute and analyzes this and automatically flags the evasion and the malicious code. Finally, we also have the DB scan clustering that this can give us additional evasions in cases where the API is obfuscated, but the condition is not. And the last thing I want to mention about our architecture is, on a high level, how the forced execution happens. So assume that the block you see at the beginning is a JavaScript file. Each small box can be a function. So the green boxes here are the functions that will execute before applying our patches. And the red boxes are the things that will not execute. So we dive inside the engine, and we make our modification in the AST level. But what are we looking for? So we're looking for conditions. So evasions happen during a condition, because that's the whole purpose. So basically, we're talking about if blocks, for loops, switch blocks, something like that. So when we detect a condition block, we dive into the block, and we're applying a DFS, depth first search, and we try to find at least one of our targeted APIs, which, as I told you before, these APIs are related to dynamic injections. If we find an API from our list, we force the whole block to execute. And this generates code for the extra blocks, and this leads to increased code coverage. And we want to mention again that this list of APIs is modifiable in case an API gets deprecated or in case a new API related to dynamic injection gets added. So this is what our results look like at a glance. So we detected 28 unique evasion categories. 5 of those were previously unreported in extensions and NPM packages, namely social media check, crypto wallet login, browser environment check, microphone, and password path check. We're gonna look at some case studies in a while from some of those categories. We also detected 110 previously unreported malicious extensions. And on average, we observe 11% increased code coverage. We also open sourced our system on GitHub if you want to take a look at this. I will show the QR code later also. So let's try to look at some case studies. So what we're looking here is what we call a time bomb evasion. That means we have a tracker of the user, and this tracker will only execute after X amount of time. The X amount of time you can see in line 12. It's the equivalent of 1 day in seconds. So what our system does is it detects the API, the set timeout API. It detects the evasion, which is the local storage object that's being stored locally, and what is the time that we need to wait. And then it sends the data to a third-party resource. And another case study that we want to take a look at is what we call a password path evasion. So here, the attacker wants to check if we're in a Unix-based system. For example, in Ubuntu, some of the passwords are being stored in /etc/password. And if this path is present, then it will take this password and it will send it in a third-party server. So the API we're looking here for is the exec API. We have the condition, and we have the malicious injection at the end that sends a post request to the third-party server. The last thing I want to mention is that we want to see how accurate our system is. So what we did is we took 500 extensions that do not have anything, and 500, they are benign extensions, and 500 extensions that have some type of evasion, and we run it through our system. And the number you probably care about here is the 2.6% of false positives. So the extensions that were flagged falsely. Overall, the takeaways of our system is that we detected 28 evasion categories. On top of that, we detected 110 malicious extensions. Our modifications are being offered as patches to V8. And because they are inside the browser modification, again, we can capture the whole chain of injections. We can always modify the API list in case this list changes. And we have tested our patches with at least 20 different Chromium versions, from 22 versions before up until the latest version up to the publication of this paper. And the last thing I want to mention is that FV8, or favorite, works everywhere that V8 is. So again, the Node.js packages, the extensions, and all the websites. And this is the QR code that you saw before with the GitHub code. And these are also our contact information, so feel free to contact us if you have any questions. And this is where I will conclude my talk. Thank you very much.